Okay, now that we've solved some non-standard maximization problems, let's take a look at solving some minimization problems that are either non-standard or do not satisfy the non-negative objective condition, which we needed in 4.2 so that when we did the dual process we could create a standard max. Now that we know how to solve non-standard maxes, we really can use either way to solve a minimization problem. We do not need to worry about having negative coefficients in the objective condition if we want to do the dual process, because we can now solve non-standard max. So right now we're going to focus on solving minimization problems the first way we solved them in 4.2, where we multiply the objective function by -1 and turn it to maximization, solve that maximization problem, and then multiply the objective value or the objective function p by -1 again to get into the minimization world. Alright, so we've done this before, it's just we're going to be doing this with non-standard maximization problems instead of standard maximization problems. So we're going to try this minimization problem, and please note it does have two variables, so you should definitely be able to solve this graphically. Since we are not using the dual process, we want to make all of our constraints less than equal. Remember, if we're going to do the dual process, we want a standard min, which means all the constraints are going to be greater than equal. Right now we're focusing on turning them into maximization problems without using the dual process. So we want to make all the constraints less than equal, and we're going to multiply the objective function by -1 to make it maximize. So our new maximization problem is going to be maximize p equals 2x minus 3y, subject to, our first constraint is already less than equal to 60, so we will leave that alone. X plus 3y less than equal to 60. Our second constraint is greater than equal to, so we'll change that to less than equal to by multiplying both sides by -1. Negative 2x minus y less than equal to -45. Our third constraint is already less than equal, so we will leave it alone. X less than equal to 40. Of course, we do have our non-negative conditions. X and y are greater than equal to 0. Now that we've created our maximization problem, we are ready to put it in an initial tableau. We have the less than equal to constraints, so we're ready to go straight into that. First constraint will be the first row. Do note we have three constraints we're turning into equations, so we do have three slack variables. Second constraint will be the second row. And our second slack variable is active. Third constraint will be our third row. One x, no y's. And that's where the third slack variable comes in. Objective function goes to the bottom. Bring everything over to the same side as p. So -2x, positive 3y, no slack variables. So we've now set up our initial tableau. Please note, we are not in the feasible region. Why? Because S2 equals -45. We have that negative constant. So, how do we get our pivot column? That's right. We find the most negative number in the same row as the negative constant. That'll be our column. So the most negative number in the same row as -45 is -2. That's our column. We now do our ratio test. Constant divided by the entry in the pivot column. 60 over 1 is 60. -45 over -2. 22.5. And then 40 over 1, of course, is 40. Since we're not in the feasible region, we choose the smallest positive ratio. There will be our pivot element. So we'll pivot in row 2, column 1, giving us the second tableau. You'll note no negative constants. That means we are in the feasible region. Which means we can now pick our pivot column by doing a standard simplex. We look for the most negative number in the bottom row. So, since we are in the feasible region, we are doing a standard simplex now. Most negative number in the bottom row is in the S2 column. So that will be our pivot column. Now, since we are standard, we do not pivot on negative ratios, leaving us with the ratio of 75 and 35. Smallest non-negative ratio will be our pivot. So that looks like we're now pivoting in row 3, column 4. We'll perform the pivot using our app or the pivot tool online, whatever you have available right now. Please don't forget about the pivot tool online. It is very handy. So we get our next tableau, and that should be our final tableau. We have no negative in the bottom. We have no negative constants. So this is indeed a final tableau. So from this tableau, we see that the maximum value of P is 80. Right here, maximum of P. That means the minimum of C is going to be negative 80. Remember, we did not use the dual. If we do not use the dual, the max of P and the min of C are opposite values. When we do use the dual, they're the same. Since we did not use the dual, we do not look at the bottom to get solutions. We just read the tableau as normal. Remember, the variables we're after are X and Y. X is active and equal to 40. Y is inactive, and therefore it's equal to 0. And if I plug 40, 0 into the objective function, I do indeed get the negative 80 for C. So that is the minimum of C. Right? This is much like the first example we did in 4.2, where all the constraints were less than equal to. The only difference here is, instead of less than equal to a non-negative, like we saw in 4.2, less than equal to a negative now. So we're just dealing with more non-standard max problems. Okay, let's look at one more problem at the top of the next page here, page 6. Okay. So again, now you'll notice this has positive coefficients and could be solved using the dual. In fact, the dual process would create a standard max. So keep in mind, before you go through the dual process, you've got to change all the constraints to greater than equal to. Okay. I'll save that for an exercise we do in one of our Zoom rooms. Right now, we're going to go ahead and solve this out as a non-standard maximization problem, which means we want to have all the constraints less than equal to, and we're going to multiply the minimization problem by -1. So we're going to maximize P equals negative 50x minus 50y minus 11z, subject to negative 2x minus z less than equal to negative 3, negative 2x minus y plus z less than equal to negative 2. Our third constraint is already less than equal, so we do not need to change it. 3x plus y minus z less than equal to 3. Of course, X, Y, and Z are not negative. So now that we have the constraints all in the less than equal to form, we're ready to create our initial tableau. So, first constraint, first row, negative 2x, no y's, negative z, our first slack variable, and negative 3. Second constraint will be the second row, negative 2x, negative 1y, 1z, our second slack variable, and a negative 2. And then the third row becomes, or the third constraint becomes the third row, 3, 1, negative 1, and our third slack variable is introduced. At the bottom goes the objective function, bring everything over to the same side as p. So 50, 50, 11, 0, 0, 0, 0. You'll note we do have a negative constant, 2 of them actually. Negative constants. Go through our negative non-standard. Non-standard simplex. So, how do we pick our column? That's right, find the most negative number to the left of the first negative constant. Our first negative constant, negative 3. Largest, or the most negative number to the left of negative 3 and in the same row is negative 2. So this will be our pivot column. We now do the ratio test. Negative 3 over negative 2 is 1.5. Negative 2 over negative 2 is 1. 3 over 3 is 1. Smallest positive ratio. We have a tie. But notice our tie is between a row with a negative constant and a row with a positive constant. In this case, we always choose the row with the negative constant. So, instead of pivoting in row 3, we're going to pivot in row 2. Row 2 has the negative constant. And it also just so happens to be on the top. We got lucky this time, but always choose the row with the negative constant when you have a tie for the smallest positive ratio. So, we'll pivot in row 2, column 1, which will give us this tableau. Note, we still do have a negative constant. So we are not yet in the feasible region. So we're going to keep going with the non-standard approach. Find the most negative number to the left of that negative 1 and in the same row. We do have a few negative numbers. The most negative is in the Z column. So Z column will be our pivot column. Do our ratio test. Negative 1 over negative 2 is 1/2. Can't pivot on a negative. A negative ratio. 1 over negative 1/2 is negative 2. 0 over 1/2 is 0. Since we are not in the feasible region, since we are still doing non-standard, that means we pivot on the smallest positive ratio. So we're going to pivot here. Okay, so let me remind us that we are still using the non-standard approach. And that's why we're choosing the smallest positive ratio instead of the smallest non-negative. It's a huge difference. Wrong choice leads a long road. Hard to get back to the right road. So pivot in row 1, column 3. That will give us the following tableau. And we still have a negative constant. So we still use the non-standard approach. So what's our pivot column going to be? Oh, there's only one negative number to the left of -1/4. So that'll be our pivot column. Column Y. Okay. So again, we still are using our non-standard approach. That's why we're not looking at the bottom row. Finding the most negative number in the same row as our negative constant. We'll do our ratio test. It's negative ratio. That's 5. And that's 1. Smallest positive ratio. So pivoting in row 3, column 2. Pivoting in row 3, column 2 gives us this tableau. And we'll note this is a final tableau. No negative constants. We are in the feasible region. And then when we look at the bottom row, no negatives in the center section of the bottom row, so we are done. This is a final tableau. It's just a center section. Your center of the bottom row. This is a final tableau. So we can now read the answer. Now keep in mind how we started. We started by multiplying the objective function of a minimization problem by -1. That means at the end we need to multiply the maximum of p by -1. This tells us max p is -111. We're after the minimum of c, so it's the opposite of the max of p, which is +111. And it's going to occur at x is active in row 2, so x is 1. Y is active in row 3, so y is 1. Z is active in row 1, z is 1. And there's our final answer. Optimal value of 111, optimal solution of 1, 1, 1, or x equals 1, y equals 1, z equals 1.